This is a video about uniform convergence of functions and also how to show a sequence of functions does not converge uniformly to a given function. So where are we? You should have watched a video about pointwise convergence of functions so far so that we could talk about this new concept. But just to remind you of that, I've got another way to think about pointwise convergence that I didn't mention in the last video. So this is more of like a kind of an epsilon definition of it that we're kind of used to playing around with if you're this far through a real analysis class. So if you've got a sequence of functions, say fn, and say their domain is some subset A of the real numbers, we say that it converges pointwise, again, to some function f on a0, where a0 is some subset of the domain of all your functions in your sequence. So we say that my sequence converges to f pointwise on a0 if and only if the following happens. For all epsilon that's bigger than 0, and for all x in a0, there should exist a natural number n such that once your indices, little n, get larger than or equal to that capital N, then your sequence ought to be within epsilon of the limit function f. And notice what this says too, the way that this is written, is that this n here, it's allowed to depend on both epsilon and it's allowed to depend on x as well. So you might need a different n depending on what point in the domain of your functions that you're looking at. So you might need a different n there. So again, n depends on both epsilon and x. And so this is kind of similar to continuity, right? So continuity was allowed to depend on epsilon and the point that you're trying to show your function's continuous at. So what I mean, delta in the continuity definition was allowed to depend on epsilon and the point at which you're trying to show the function's continuous. Remember, we had that stronger notion though with continuity that was called uniform continuity that said you should be able to find a delta that only depends on epsilon. So what we're going to have here is a similar notion for the convergence of functions. What if I once, is it possible that maybe this index only depends on epsilon? That would be a much stronger thing. And so what are we going to call that? We're going to call that uniform convergence. So I have these two concepts. I have pointwise convergence and I have uniform convergence. So we'll say that the sequence fn converges uniformly to f if and only if the following happens. And so I'm going to write down a very similar kind of epsilon definition like this. And if you just compare the two, so for all positive epsilon, now there exists an n. So notice I don't specify that for every x in your domain you have to be able to find an n, right? I don't say that. So I just say right here, capital N only depends on the epsilon that you have, such that again, once you get past that index capital N, then again it says that the sequence and the limit value should be within epsilon of each other. And again, this should be true for every single x. So again, there's one n that should make this happen for every single x in R. Or not in R, but in your domain A0. And so again, like I just said, in that case, for uniform convergence of functions, the n only depends on epsilon. It cannot depend on the point x in the domain. So that's a big difference. That's the big difference between uniform and pointwise convergence for right now. And so some notation that goes along with it, if you see these double arrows, that means that the sequence of functions fn uniformly converges to this function f. And if I think about this definition, if this is true, for every epsilon bigger than 0, there exists an n such that once I get past that, this happens. That implies that this happens. That says, well, for every epsilon and for every x, I could find an n. Well, if I assume this down here, then there's one n rather that works for every x. So what I'm trying to say is if you know that this happens, that implies that this happens. And so what does that mean then? That means that uniform convergence implies pointwise convergence. And again, this is that idea that uniform convergence is kind of a stronger notion. If a sequence of functions converge uniformly, then they converge pointwise to that limit as well. But what's not true is the other way. So pointwise convergence does not imply uniform convergence. And we'll talk about that in a little bit in this video. Let's do an example though. So how do I use this definition of uniform convergence here? So what I claim is this sequence of functions, sine of nx plus n, all divided by n, converges uniformly to the 0 function for every x in the real numbers. So I want to try to set this up kind of similarly to how we always do epsilon proofs, where I'd write down the definition first and write it down so that I see, my functions And I want to show that this difference here is less than epsilon. So like, how do you usually start these kinds of things? You usually start screwing around with this to try to see if you can whittle this down to some relationship between an epsilon and an n. In this case, a little n. So this one's not too bad, because if I start on that side, I'll just copy paste this down here, and I won't bother writing the minus 0. What I'm going to do is I'm going to rewrite that as, that's the same thing as 1 over n times the numerator. And let's see, I could split that absolute value up. Remember, 1 over n is positive, so it doesn't need an absolute value, but this would be 1 over n times the absolute value of sine. And what do you know about sine, the absolute value of sine? Well, I know that this is bounded by 1. And so this is less than or equal to 1, and I know it's bounded by 1 for every single input x. So for every x and r, that inequality is true. So far, what have I got? I've got that the difference between sine of nx plus n, maybe it would be more appropriate, I know that this difference between my sequence and 0 is less than or equal to 1 over n now. So what does that tell me? Why don't I just make sure that my natural number is bigger than 1 over epsilon? So to put it all together, what have we got? Here's what the proof of this result would look like. Let epsilon be a positive number. We're going to choose a natural number n such that n is larger than 1 over the epsilon that somebody gives you. Then, for every natural number little n bigger than capital N, we see the difference between my sequence and 0 is less than or equal to n. And so here I'm just kind of hand waving all the work that I did here to show that inequality. But that 1 over little n, of course, is going to be less than or equal to 1 over capital N, right? Since capital N is a smaller denominator than little n. And of course, if n is larger than 1 over epsilon, then when you take reciprocals of this, you should get that 1 over n is less than epsilon. And remember, that holds for every single real number x, right? Everything that I've done here did not depend on the x that I've plugged in. Therefore, this inequality is true for every real number x. So that is how you would show that, again, this sequence of functions converges uniformly to 0. Nowhere did when I chose n here, n did not have to depend on the x that I was considering. This argument worked for every x. So how do we show that the sequence of functions does not uniformly converge to a given function? So we'll say that a sequence fn does not converge uniformly to a function f if and only if the following happens. So there exists a particular epsilon, call it epsilon naught or epsilon sub 0, and a subsequence of your sequence of functions, call that subsequence f sub nk, and a sequence xk of points that are in the domain of your sequence of functions and the limit function, such that, and this could be kind of similar to how we showed that a sequence doesn't converge earlier, I should have that the difference in the outputs should be greater than or equal to that particular epsilon naught for every single k. So in other words, I should infinitely often kind of bounce out of that window of radius epsilon naught that's supposed to surround this limit point here. So there are infinitely many such points that bounce out of the window of radius epsilon naught around the value f of xk. So let's do an example about how to use this. So let's let f sub n, my sequence of functions, be x over n. I talked about this in a previous video, in the other video that I made so far about pointwise convergence. And let's say that f is the 0 function. So f of x is 0 for every real number x. So recall I showed in that video that x over n, converges to 0 for all x and r. And remember, when I use this one arrow here, that means it converges pointwise, is what I'm trying to say. So x over n converges pointwise to 0, but what we're going to show is that x over n does not uniformly converge to 0. So how are we going to do that? Well, we're going to use this criteria up here. We need to be able to find an epsilon, find a subsequence of our functions, and find a sequence of points in the domain. So I need to pick an epsilon, find a subsequence of these, and my domain is real numbers, so I just need to find some sequence in there, such that, though, the difference between these two values is always bigger than or equal to that epsilon. So what I'm going to do is I'm going to let epsilon not be 1. And then now, what would be nice? Well, let's see. What if I took a subsequence here? I know that this is 0 all the time. Could I make this? Is there a subsequence of my functions and of inputs that would make this, say, some constant, say 1? So why don't I let nk just be k for all natural numbers k? Why don't I let xk be k as well? So then, what have I got? What would the subsequence of functions with these indices and these inputs look like? That would just be, well, xk over nk, right? That's what fn does. It takes the input and divides it by where are you at. So if I plug my stuff in though, that's k divided by nk is also k. And so you get 1. So what have I got then? I've got a subsequence of my functions whose output on this sequence xk is always 1 no matter what. And I think you probably see where this is going. What would f of xk be? Well, f is supposed to be 0 for every real number, so f of xk is going to be 0 too. And so what have I got? I've got that the difference in absolute value between fnk of xk and f of xk, that's the same thing as 1 minus 0. Well, that's equal to 1. So in particular, what have I got? I've got that my sequence never gets any closer than 1 to the proposed limit. And so that is the idea that this sequence of functions does not converge uniformly. So what we just did is, again, we verified that something bad like this happens. And maybe one more time, I've got some window of radius epsilon naught around f of xk here, and I just showed that I've got a subsequence that bounces out of there infinitely often. And in this case, this subsequence is in fact always outside of that window of radius 1 around 0. So fxn does not converge uniformly to 0 on R. So again, uniform convergence is a little bit harder to do. And so you see as well, pointwise convergence can be fine, but that does not imply uniform convergence. Remember up here, we said the other way around is true. Uniform convergence does imply pointwise convergence.